All right, good morning. Moving on, 4.3, we're going to take a look at derivatives now. Remember, we're thinking about derivatives as their own functions now. The derivative of a function is its own function. And how do the derivatives affect the shape of a graph? What can we tell about the shape of a function by the shape of the derivative, and vice versa? What can we tell? We're going to be looking at a number of different tests. We're going to introduce some new ideas and some new concepts, some new words here. And we're also going to look at some things that should be fairly familiar when it comes to maximums and minimums, and things that we haven't maybe thought about yet, but things that we probably should realize already. All right, so let's start by talking about a particular test. The first test we're going to talk about is increasing and decreasing test. And in the increasing and decreasing test, we're going to be able to tell whether a function is increasing or decreasing over different parts of its domain based on the derivative. If the derivative of the function f prime of x, if the derivative is greater than 0 for all x on some interval, then think about it. If the derivative is greater than 0, that means the slope of the tangent lines are positive. If all the slopes of the tangent lines are positive, then the original function is increasing on that interval. Similarly, if the derivative is less than 0 for x on some interval, over some interval, what does this mean? It means the slope of the tangent lines are negative, negatively sloped tangent lines. Then the function is decreasing on that interval. If the tangent lines are positive, then the function is increasing. If the tangent lines are negative, the function is decreasing. Well, what if the derivative is 0? What if the derivative is actually equal to 0? Well, then it's not increasing nor decreasing. It's staying the same. It's constant. And usually we think about that as a maximum or minimum point. But recently we changed that idea and started talking about it as a critical value, and we'll see that there's actually a secret third option, that it doesn't have to be a maximum point or a minimum point. So let's take a look at this test. Let's apply it. Let's look at a couple of applications of this test. So first, consider the following function. F of x is equal to x squared plus 6x, and I want to know, is this function increasing on the interval from -1 to 2? Is it increasing over that interval? Well, as you can imagine, the first thing I need to do is find the derivative. So the derivative of my function is 2x plus 6. And I want to see, well, what's happening at -1 and at 2, at the endpoints here. So at x equals -1, the derivative at -1 is 2 times -1 plus 6. -2 plus 6 is positive 4. At x equals the other endpoint 2, the derivative at 2 is going to be 2 times 2 plus 6. 4 plus 6 is 10. So my derivative is positive and positive. So it's going to be positive throughout here. So the answer is going to be yes. This function is increasing throughout this interval right here, from there to there, the derivative, because all of the tangent lines are going to be positive. Well, let's take a look at another example question, and this time we'll ask ourselves to find more information about it. Suppose I'm given a function f of x equals x cubed plus or minus 3x squared. And I want to know, where is this function increasing and decreasing? Over what intervals is this function x cubed minus 3x squared, that's a minus, 3x squared, where is it increasing or decreasing? And as you can imagine, the first thing we're going to do is we're going to start by taking the derivative of the function, and I'm going to get 3x squared minus 6x. And I don't have an interval here, so I'm very interested in seeing, well, where is this equal to 0? So if I set it equal to 0, 3x squared minus 6x, factor out of 3x, x minus 2, and I get x equals 0, x minus 2 equals 0, and x equals 2. So interesting things are happening at x equals 0 and x equals 2. Things are changing. The slope of the tangent line is 0 at those points. So I want to take a closer look at, well, what does this mean in my function? So in my function, I'm going to create a table now, and I'm very interested in the intervals from, so I'm going to look at my function, and I want to look at the derivative, but I'm very interested in looking at the derivative from negative infinity to 0, and then from 0 to 2, and then from 2 to infinity. And when I know what's happening here, I will know more about my original function. All right, so in this interval from negative infinity to 0, what's happening with my derivative here? If I pick, here's my derivative. If I pick a value less than 0, something like a negative 3, and I plug negative 3 in here, negative 3 squared times 3 minus 6 times negative 3, I'm definitely going to get a positive number here. My derivative is going to be positive in that interval. How about between 0 and 2? Pick a number like 1. If I plug 1 in here, 3 times 1 is 3, minus 6 times 1 is 6. It's definitely going to be negative in that interval. And how about between 2 and infinity? Pick a number in here, a test value in here like 10 or something like that. 3 times 10 squared minus 6 times 10, it's definitely going to be positive. So, well, what does that tell me? Well, if in this interval, my derivative is positive, then my function is increasing. Here, my derivatives are all negative, so my function is decreasing. Here, again, all of my derivatives are positive, so my function is increasing. I actually know something else, that at the point 0 and 2, I've got some interesting things that are happening. What's happening at the point x equals 0, and what's happening at the point x equals 2? Well, my derivatives are going from positive to negative. My function is going from increasing to decreasing. So what's happening here at 0? I must have a maximum value happening right there. Here, my tangent lines are going from negative to positively sloped. My function is going from decreasing to all of a sudden increasing. So I must have a minimum value here at x equals positive 2. So I know a little bit more. Not only do I know where my intervals are increasing and decreasing, but when it changes from increasing to decreasing, I know I've got a maximum. When it's changing from decreasing to increasing, or the slope of the tangent lines are changing from negative to positive, I know I'm going to have a minimum value there. This brings us to something called the first derivative test. So all of this stuff that I think we probably already realized, we probably already know, let's make it very formal, and we're going to call this the first derivative test. Now the first derivative test tells me this. If the derivative of the function changes, so my derivative, the slopes of the tangent line, changes from positive to negative, what's happening? At some point C, so if the derivative is changing from positive to negative at some point C, then what's really going on at C? Well, then the function, the original function f of x, has a maximum at C. Similarly, if the first derivative is changing from negative to positive at some point C, then, well, what's happening here? If it's changing from negative to positive, then I'm going to have, then f of x has a minimum at C. But now there's another possibility here. What happens if the derivative does not change signs, does not change signs from negative to positive or from positive to negative at some point C. So it was positive going into C, and then it's positive coming out at C, but at C it could have been 0. So it's positive on both sides of C, or it's negative on both sides of C. Well, then the function does not have a max or a min at point C. And this is kind of a whole secret third option, a whole nother third possibility here, where I could have a 0 tangent, but it might not be a maximum or a minimum. Let's take a look at an example. I've got an example where we can see this a little bit more clearly. Suppose I'm giving the following function. F of x is equal to 4x cubed minus x to the fourth. And I want to find the local max and minimum points, and I'm going to use it using the first derivative test. So obviously the first thing I want to do is I'm going to take the first derivative here. So the derivative of the function is going to give me 12x squared minus 4x cubed. Set that equal to 0. 0 equals 12x squared minus 4x cubed. It looks like I can factor out a 4x squared, and I'm going to get left with 3 minus x. Set those equal to 0. 4x squared equals 0. X squared equals 0. X equals 0. There's one critical value. 3 minus x equals 0. 3 equals x. There's my other critical value. So I've got two critical values here. I've got two critical values. Now let's explore what's happening at each of these critical values. So again, I'm going to create that data table. I'm going to look at my data table, and I want to look at the derivative, and I want to look at the intervals from negative infinity to 0. and then from 0 to 3, and then from 3 to infinity. And that's going to tell me about my original function. All right, so picking some test values. If I pick a test value in here, something like negative 73 or something like that, and plug that into my derivative here, I'll save you a little bit of time. When I take a big negative number and cube it, big negative times a negative is going to be negative, so it's going to be positive here, and negative times a negative is a positive. It's definitely going to be positive right here. It's definitely going to be positive. Between 0 and 3, pick a number like 1. If I plug 1 in here, 12 minus 4, I'm going to get a positive number as well. If I pick numbers bigger than 3, something like 100. If I pick a really large number in here, this is going to become really, really, really big, and this is going to be negative. So what does that tell me about the original function? It tells me that it is increasing over this interval. It is also increasing here, and it is decreasing there. But now let's take a closer look. What is happening at x equals 0 and x equals 3? At x equals 0, my function was increasing, and then all of a sudden I've got 0 tangent line, but it's increasing after that. So increasing, there was no change. It didn't change from increasing to decreasing or decreasing to increasing. So this is no maximum or minimum point. There's no maximum or minimum point here. It's not a maximum or minimum. What about over here? Here at 3, I'm changing from increasing to decreasing. My tangent lines are changing from positively sloped to negatively sloped. Obviously at 3, I'm going to have some sort of maximum value. But the key here is that at 0, it's not a maximum and it's not a minimum. You know, well, what would that look like? How is that possible? Let's take a look at it. So here's the algebra behind it. Let's take a closer look at it and look at a couple of graphs. Maybe if we looked at some graph examples, we might be able to spot it a little bit better. So in my first example, suppose I have a nice well-behaved function, something like this. And clearly we can see that my tangent lines, I've got some point here, C, and my tangent lines, where's my little, my ruler? My tangent lines here, negative, 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 0, positive, 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 positive. So at C, the slopes of the tangent lines, the first derivative is changing from being negative to positive. Over here, if this is my original function, f of x, on this side, the derivative of f of x is less than 0. On this side, the derivative of f of x is greater than 0. Negatively sloped lines, positively sloped lines. I've got a minimum value right here. All right, let's take a look at another possibility. And of course, I could flip it upside down and make it a maximum going from positive to negative. I don't want to do that one. That one's not very interesting at all. But I do want to take another look at a possibility, that other strange possibility that I could have. And here in the function, this time I want to look at the following function. Something like this, almost like some sort of cubic that's been moved up and over the notice that if I look at my tangent lines, positive, 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 0, positive, 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 and I'm using the edge of the protractor to represent that. But again, I've got this point somewhere right around here at some sort of C, critical value, where the tangent line is 0, just like the tangent line was 0 here. But notice on this side, and this is my function, my f of x. But on this side, the derivative of f of x are all nice, well-behaved positive numbers. My tangent lines are positive. On this side of C, they're still positive. So it didn't change. The tangent lines are positive, 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 0, positive, 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 positive. So here, there is no max or min. This is not a maximum or a minimum point. There's something else going on here. This is an important point, but it is not a change in the derivatives from positive to negative or negative to positive. All right, let's take a look at one more graph. This one I'm going to ask you to sketch down a kind of a strange graph, and then we're going to kind of rip it apart and talk about it. Here it is. And for this graph, at -1, and then +1, 2, 3, and 4. At -1, I want to have an x-intercept. At 1, I'm going to have some sort of maximum value up here. At 3, I want to have an x-intercept, and at 4, I want to have an x-intercept. And I want the graph to look something like, let's see if I can draw this in here. So, something like that. So I've got definitely a maximum here, an x-intercept here, an x-intercept here, an x-intercept here, some sort of minimum value. And notice this is a corner or a cusp as well. But this is not a function. This is actually the derivative. This is a function of the derivative of some other function. So this is not the actual function. This is the derivative. And as we take a closer look at this, I want to see, well, what's happening here? And what can I tell about my original function based on the graph of the derivative? Well, let's see. The first thing I should be able to tell is that the original function is decreasing from -infinity to -1. How do I know that? Because the tangent lines, remember this is the derivative, the tangent's negative here. The tangent lines are negative. They're less than 0. So the original function has to be decreasing. What's happening from -1 all the way till 3? All of the tangent lines are positive, so my original function, I should say f of x here, is decreasing. F of x is increasing from -1 to 3. Between 3 and 4, everything's negative, so again I'm going to have interval of decreasing in my original function from 3 to 4, and then from 4 on, my tangent lines look like they're positive, so back to increasing from 4 to infinity. All right, so now knowing this, what else can we tell about the original function? Can we tell where the original function has some maximums and minimum points? Well, let's take a look at this. Here, my derivative is negative. So it's decreasing. Here, you know what, let me write that down. The derivative here was less than 0. My derivative is greater than 0. My derivative is less than 0. And my derivative is greater than 0. So, given all this information here, what do I know? What's happening at -1 in the original function? My derivative is going from, I'm going from decreasing to increasing. I'm going from negatively sloped lines to positively sloped lines. So, I'm going to have a minimum at x equals -1. What's happening at 3? Well, I'm going from positive to negatively, so I'm going to have a maximum value at x equals 3. And what's happening at 4? Well, at 4, it looks like I'm changing from negative to positive. It looks like I'm going to have a minimum value at x equals +4 in the original function. All of this is in the original function. All right, so a lot of things that we can tell just by giving the graph of the function. When we come back in the second part of today's lesson, a little bit longer, we're going to talk about concavity. I noticed we talked briefly about that before, but I want to be a little bit more formal, and we're going to look at the concavity test, and we're going to look at something called the second derivative test in the next part of the lesson. So if you want to pause, go straight on to the next part of the lesson. I'll talk to you again soon.